Yes, hello everyone. Welcome on YourPedia platform. I am Vishal Sharma, and as you all know, guys, we have launched this NPTEL assignment series for upcoming GATE examination. And through this series, guys, we are discussing important concepts and some very important NPTEL assignment questions we are discussing. Okay, so I think this is my third lecture this year for NPTEL series, and soon we are going to start the marathon series also. Students, they are placing their request to start some kind of marathon class, and yes, soon from next week we are planning to start some kind of marathon classes. Okay, so in today's session, guys, we are going to solve very important, very good question actually from Rankine cycle. Okay, so if you are having this particular NPTEL assignment booklet with you, okay, in this mechanical assignment booklet, in chapter 2.3, question number 12, 13 and 14 you are going to find out. Okay, question number 12, 13 and 14 from this assignment, NPTEL assignment mechanical engineering, chapter 2.3 Rankine cycle. Okay, so we are going to solve actually this particular question from Rankine cycle, and very typical actually gate level question and very important concept we are going to recall, discuss through this question, guys. Okay, I hope you will like this question at the end. Okay, chaliye, so this is actually a common data question. 1, 2, 3 are common data question. Let us first read the question and then we will start solving. It's my request, suggestion to all of you guys. If you want to try this question, it is good to give a try. You can pause this video and you can try. Okay, if you are getting solution, you can skip some of the part of this video and you can match your answer. And if you are not getting the answer, guys, then obviously you need to watch this entire video and you need to think where you are making the mistake, because analysis is very important, guys. If you are preparing for GATE, if you are making mistake, there is no such problem. If you are practicing, you are appearing in some mock test and you are not getting good marks, there is no such issue, guys. But you need to, on daily basis, you need to analyze your performance and you need to improve gradually, whether it is 1%, 2% or 5%, but you need to keep on improving, guys, if you want to score very good score in this upcoming GATE examination. Chaliye, there is a steam power plant in a region operates on a real Rankine cycle. Real Rankine cycle, guys, this point is very important. Real Rankine cycle. So the cycle is not operating on standard Rankine cycle, it is operating on real Rankine cycle, and not exactly real. Okay, real doesn't mean exactly real, means he has given you isentropic efficiencies of turbine and pump, so those you need to consider. But in real, actually, real case, the pressure drops also going to take place in the boiler and condenser. Those things we are not going to consider. So real means only we are considering the isentropic efficiencies of turbine and pump. Fine, has a net power output. So net power output is given to you, 60 megawatt is a net power output. Steam enters the turbine at 7 megapascal, 500 degree Celsius. So there is a steam table given, saturated water and superheated steam table. So this is saturated water steam table. You can check it here at 7 megapascal. What is T saturation, guys? At 7 megapascal, T saturation is 285.829. It means the steam which is entering into the turbine, it is a superheated steam, because the temperature of the steam is much higher. It is higher than the T saturation. And you know, if T saturation, temperature is more than T saturation, it means the condition of the steam is superheated. It is cooled in the condenser at a pressure of this. So boiler pressure is given to you, steam entry temperature is given to you, condenser pressure is given to you, and heat is rejected in the condenser by running cooling water from a nearby lake through tubes of condenser at a rate of this. So rate of cooling water is given to you 4000 kg per second. If the isentropic efficiency of the pumps and turbine are these, 75% is the isentropic efficiency of pump, 80% is the isentropic efficiency of turbine, then he is asking you in first question, first part, he is asking you the thermal efficiency, means the cycle efficiency, Rankine efficiency, guys. Efficiency of Rankine cycle or cycle efficiency. Cycle efficiency he is asking you. So you need to calculate the Rankine cycle efficiency. Got the data, guys? I hope it is very clear. So the data is given to you. This is first part of the data. And some more information he has given you, guys. Let me move to that also. This is another information. This is a steam property table related to what? Superheated steam. Earlier one was the property table related to saturated water, saturated steam. Okay, and now this is a property table related to superheated steam. So 7 megapascal, 500 degrees Celsius, the specific volume of the steam will be this, internal energy will be this, enthalpy will be this, entropy will be this. All standard units. Okay, units are also mentioned. So this is actually a standard Rankine cycle, guys. If you refer to this diagram, this is standard Rankine cycle. 1 to 2 isentropic compression or pumping process. 2 to 3 is the heat addition, constant pressure heat addition in the boiler. Okay, this is heat addition in the boiler, heat addition. Okay, 3 to 4 is the expansion process in the turbine. Isentropic expansion, ideally standard, but in real case, because he has given you the isentropic efficiency, so the expansion will be something like this, Okay, so this is 4 dash, this is 4 dash. Similarly, 1 to 2 is the isentropic compression or pumping process, but in this case, because the isentropic efficiency of the pump is given, okay, this is actually a straight line, guys, something like this. So here also the point 2 you are going to get somewhere here. So this is point 2. Are you getting some idea, guys? So this is point 4. The expansion is going to take place from 3 to 4 dash. Here the compression or pumping will take place from 2 dash to 1. 1 to 2 dash. Fine. So properties are given and he is asking you the isentropic efficiency. So please try, guys. If you want some hint, but first it is good to try without any hint. So you can try, you can pause the video, you can try, and if you want some hint, guys, let me write it here, the cycle efficiency. Okay, so Rankine cycle efficiency is nothing but W net work divided by heat supplied. Net work by heat supplied, this is the cycle efficiency. Now what is net work, guys? It is WT turbine work minus WP pump work divided by heat supplied. So which work you will take? Isentropic turbine work, isentropic pump work, or actual turbine work, pump work? Obviously, if you want to calculate the cycle efficiency and he has given you the isentropic efficiency, so you need not to consider the isentropic compression or expansion. You need to consider what? The actual expansion and compression. That's why this WT minus WP will be what? Actual turbine work, actual pump work which you are giving to the pump, okay, which will be slightly more than the isentropic work given to the pump, divided by heat supplied. Now, what will be this, guys? What will be this turbine work, actual turbine work? So this will be H3 specific enthalpy. Let me write all these things in specific term. So H3 minus H4 dash. Fine. Getting idea, guys? H3 minus H4 dash. This is the turbine work. Minus, not H3 minus H4. H3 minus H4 is the isentropic work. Okay. When the expansion is taking place isentropically. But in this case, the expansion is not taking place isentropically. Okay. It is a non-isentropic process. Okay. So H3 minus H4 dash. What is pump work, guys? Pump work will be H2 dash minus H1 divided by heat supplied. What will be a heat supplied, guys? This is a heat addition process. In standard case, heat addition is 2 to 3, but in this case, because the exit of the pump is what? 2 dash, so the heat addition will be H3 minus H2 dash. H3 minus H2 dash. So if you're able to find out all these enthalpies, you will get the answer very easily. So question look like very simple, but yes, you need to pay attention, you need to think how you're going to get all these enthalpies, because he has not directly given you these data. Some data is available in this property table and some data you need to evaluate. Okay, now the question arises from where you will get H3, guys. H3, what is H3, guys? H3 is the enthalpy of the superheated steam at the entry of the turbine. The steam enthalpy at the entry of the turbine. And what kind of steam is entering? The superheated steam is entering at pressure 7 megapascal, at temperature 500 degrees Celsius. So what is that enthalpy, guys? So that enthalpy is directly you can use, that directly you can refer to the superheated property table, superheated steam property table. So H3 is directly given to us. This is the enthalpy, kilojoule per kg. Fine. Okay. Now, what is next? Next is what? H1. What is H1? H1 in this data, H3, H1. What is H1? H1 is the enthalpy of the what? Saturated liquid at the exit of the condenser or at the entry of the pump. So HF. What is H1, guys? H1 is nothing but HF at the rate of what? Condenser. Okay, T condenser. So what is condenser? Condenser conditions are what? This is the pressure, condenser pressure. This is the saturation temperature at the condenser, and this is HF, guys. HF 191.8. Okay, 191.8. This is HF. You can take some kind of screenshot, you can note it down, you can pause, you can note it down this entire data, and then you can start practicing with me. Okay, so H1 is how much, guys? H1 is 191.8. Fine, let me write it here, 191.8 kilojoule per kg. Good. Now next is what, guys? H3, H2 dash, H4 dash, H2 dash and H4 dash, H2 dash and H4 dash. So from where you are going to evaluate these two enthalpies, H2 dash and H4 dash? Fine. H2 dash and H4 dash. So guys, here for evaluating these two enthalpies, you need to consider the isentropic efficiencies of turbine and pump. Let me consider here first the isentropic efficiency of pump. Okay, so pump is a work absorbing device. You are giving work. So what is that isentropic efficiency of pump, guys? This will be the this isentropic work given to the pump divided by actual work given to the pump. Isentropic efficiency of the pump is nothing but isentropic work given divided by the actual work given. So how much is isentropic work given, guys? This is nothing but specific. In specific term, you can write it as H2 minus H1. How much is actual work given? This is H2 dash minus H1. And this is nothing but what? 0.75, because the isentropic efficiency of the pump is given to us 75%. Okay. So in this case, what we know? We know this data. We know H1. What is this H2, guys? H2 is not directly known to us, but we can evaluate this. We can evaluate this H2. Okay, H2 we can evaluate. How you can evaluate this, guys? You need to think. I'm giving you some time, 10-20 seconds. You need to think from where you are going to get this H2. Let me show the diagram, guys. So H2 is this. H2 is the enthalpy of the liquid. Obviously, at the entry of the boiler, you are having liquid only, sub-cooled liquid. So there are some, direct, you can find out this HF using what? HF will be nothing but what? The enthalpy of the liquid in the sub-cooled region. You can approximate it as HF at same T saturation. But those are kind of approximation only. Okay. In real case, actually, to get the more accuracy, we need to evaluate this, we need to calculate this, and from where you are going to get this, guys? H2 dash. For that, what you need to do, guys? You need to take the pump work. So let me write it here, the pump work, WP. So what is pump work, guys? Isentropic pump work. Isentropic pump work is nothing but H2 minus H1, and isentropic pump work you can write it as VDP, where V is the volume, volume of what? The liquid at the entry of the pump, V1. Okay, into the dP, change in pressure, so that will be the boiler pressure minus condenser pressure. Fine. So WP, pump work, will be H2 minus H1, that is equal to V1 into PB minus PC. So now what is H2? H2 equal to H1 plus V1 into PB minus PC. So from this equation, guys, you are going to get the H2. Enthalpy at the isentropic enthalpy. Okay, if the compression is going on isentropically, so enthalpy at the exit of the pump if the compression process is isentropic. Otherwise, in real case, the enthalpy which you are going to get, that will be H2 dash. So H2 will be known to us from this equation, because if you refer to this, this is 191.8 plus. What is V1, guys? Let me again put it here, the data in front of you. V1 is this. V1 is nothing but VF at condenser pressure. So this is 0.00101. Okay, आगे भी further आप ले सकते हो. So this value I'm going to write it here. Okay, so this is let me write it here. 0.00101.027. Okay, this I'm taking in kilojoule per kg. So this is in meter cube per kg. Okay, specific volume. So this also you need to take in what? Kilopascal. So how much is the boiler pressure? Boiler pressure is 700 kilopascal, 7 megapascal. So you can write it as 700 kilopascal minus 10. So solving this, guys, you will get the H2. You can solve this, you can check your calculation, what answer you are getting for the H2. Fine. So let me also carry out the calculation for you, and you can also match your answer. Condenser pressure is given to us 10 kilopascal. Okay. Fine. Plus 191.8. Actually, that's why I mentioned directly also you can take it as HF only, but some kind of error you can get. So adding this, the value will come out very close. Okay, and it will be this plus 191.8. Okay, so it will be 192.497 kilojoule per kg. Fine guys, now you can put this value here and you can tell me the value of H2 dash. So H2 dash will be H1, okay, H1 plus this value H2 minus H1 divided by 0.75. So H2 dash will be 191.8 plus, what is this? This is 192.497 minus 191.8 divided by 0.75. So you can check your answer and you can match what value of H2 dash you are getting. Okay, fine guys, please check your answer. Obviously pump work is very less, pump work is going to come out very less, but yes, you need to consider, we need to consider that also. Okay, हमें consider तो करना पड़ेगा बच्चों. Obviously it will come out very less because this pump deals with the liquid and liquid specific volumes are very less. Okay, 700 and this 10 kilopascal. Fine, I hope you all are getting, you can match your answers. Okay, so solving this you will get in value close to 192.72 kilojoule per kg. Fine guys, so we are having H2 dash, we are having now this H2 dash we are having, we evaluated this. Now from where you will get this H4 dash guys? From where you are going to get H4 dash? Please check and tell me where you are going to get H4 dash. So for this also guys, what you can do? You can write it here, the isentropic efficiency of turbine, which is nothing but what? How you can define the isentropic efficiency of turbine? So this is nothing but the actual work developed by the turbine divided by isentropic work developed. So the actual work developed will be what? This will be H3 minus H4 dash. The isentropic work developed will be H3 minus H4. Turbine is a work producing device. So for turbine, isentropic efficiency will be the actual work produced, obviously which will be lesser. The actual work produced will be lesser than the isentropic work. Efficiency will always be less than 100% guys. Okay, isentropic efficiency, so you can check it here. So actual work divided by isentropic work. So this is H3 minus H4 dash divided by H3 minus H4. So now again, you know the H3 and from where you are going to get H4 guys? H4, this is not again directly known to us, because what is H4? You can check it here, this diagram. What is H4 guys? H4 is the enthalpy of the wet steam. This 4 is in the wet region, 4 dash is also in the wet region. Okay, you cannot take it as Hg at the condenser pressure. Obviously it will be very close to that, but you cannot say, because efficiencies values are very close. You can check it here, 31%, 24.5, 29.2, 32.5. These values are very close. And even suppose if you are getting some kind of numerical answer type question, then there will be huge error guys. You will not get the right answer if you are approximating H4 dash with Hg at condenser pressure. You cannot take like that. So you need to think from where you are going to get H4 dash guys. H4 dash you will get from this equation, but from where you will get H4? H4 is also in the wet region. So what you need to do guys here, you need to equate S3 with S4, because isentropic expansion, when it is taking place, the entropy at the entry of the turbine S3 will be equal to the entropy of the wet steam at the exit of the turbine. So H3 equal to S3 equal to S4. So what is S3? S3 is the entropy of the superheated steam. You can refer to the superheated steam table here. This is this 6.8. This is the entropy of the superheated steam. Okay. So you can write it here 6.8. And what is S4, guys? S4 will be the entropy at the exit of the turbine, and that you can write it as SF plus X SG minus SF at what? At condenser, at the rate of T condenser, guys. At the rate of T condenser. So at condenser temperature, you can check it here. You can refer to the saturated property table. You can check it here at condenser condition, condenser pressure, condenser temperature. This is SF, this is SG, this is SFG. So all things are given to us in the property table. Okay. So putting all these values here, you can refer to the table, and by referring to that table, you can easily evaluate the dryness fraction, guys. So you can check your answer. I'm just mentioning here the dryness fraction which you are going to get. If you solve this, this will come out 0.82015. 0.82015. So 82% is the quality. 82% close to that is a vapor. Remaining is what? Liquid. Okay. So quality of the steam is 82%. 0.82015 is the dryness fraction. Now, if you know the dryness fraction, then what you need to do? You need to write it here H4. H4, because H4 will be what? This will be HF plus X Hg minus HF, again at what? At T condenser. So T condenser, condenser temperature pe, you know HF from the property table, you know Hg, you know HF, and X we evaluated, which is 0.82015. You will get the H4, guys. Using this equation, you will get the H4. Fine. Okay. H4 you are going to get from this equation. Okay. Now, if you know the H4, if you put it here, H4, isentropic efficiency of the turbine is 80%, you will get the H4 dash. Okay. You will get the H4 dash. So guys, please check your calculation and try to match your answer what value you are getting for this H2 dash. I hope this is very much clear now, guys. That calculation you need to do. H4 dash, the enthalpy of the wet steam actually at the exit of the turbine when the expansion is not taking place isentropically. Similarly, what is H2 dash? H2 dash is the enthalpy of the liquid, okay, going out of the pump when the compression is not taking place isentropically. So that is H2 dash and H4 dash. I hope those points are very much clear how to evaluate H2 dash and H4 dash. The formula is very clear. Isentropic efficiency expression you need to use, but in that also you need to first think how to evaluate H2. H2 you are going to get from what? H2 minus H1, the pump work, that is equal to V, the specific volume which pump is handling, into the dP, change in pressure, which is boiler pressure minus condenser pressure. Similarly, what is H4? H4 you are going to get from the HF here, H1 plus X Hg minus HF at the condenser condition, but for that you need to evaluate the X value dryness fraction, and that you will get by equating S3 with S4. Okay, I hope all these enthalpies are very much clear to you now, and if you know all these enthalpy, guys, H3, H4 dash, H2 dash, H1, H3, H2 dash, easily you will get the cycle efficiency. Now you can match your answer and tell me what answer you are getting for this question number 1, guys. 4 options: 31%, 29.2%, 24.5% and 32.5%, guys. Please tell me what answer you are getting. So guys, if you solve, if you put all the values, you are going to get the cycle efficiency close to 31.04%. 31.04%, close to this efficiency you are going to get. That's why we can go with what? Option A as the right answer. Okay. Option A will be the right answer for this question. Fine. And guys, you can check it here by evaluating this thing. You can mention it here what W net you are getting, because the numerator term, this numerator term is nothing but what? W net, and this denominator term is giving us what? Heat supplied. So you can tell me how much W net also you are getting, guys. You can tell me how much W net you are getting. And this W net will be in what, guys? What will be the unit of this W net? It will be in kilojoule per kg. Because we are not using mass of steam, so W net also you can tell me H3 minus H4 dash, the actual turbine work minus actual pump work, that will give you the W net actual in kilojoule per kg. Okay, I hope this part 1 is very much clear to you. Now let us move to the part 2. Okay, so with reference to the question number 1, determine the mass flow rate of steam. Determine the mass flow rate of steam. Now guys, what he has given you? He has given you W net. The net power output of the plant is 60 megawatt. Okay, this is the net power output of the plant, 60 megawatt. So you can write it in kilowatt. Okay, so guys, you know, kilojoule per kg into kg per second, this is nothing but what? Kilowatt. Yes or no? Okay, so this W net in 60 into 10 ki power 3 kilowatt, you can equate with W net, which we evaluated in what? In kilojoule per kg into the mass of steam. Okay, so this is given to us, the net output of the plant, the net power output of the plant is 60 megawatt, but you need to write it in kilowatt. So 60 into 10 ki power 3 equal to W net in kilojoule per kg multiplied by the mass of the steam, you are going to get in kg per second. So please do your calculation and check what answer you are getting. So W net will be this term, this numerator term will give you the W net in kilojoule per kg. Okay, so that we already calculated. So 60 into 10 ki power 3, you need to divide it by W net, you will get the mass of steam. So please check and tell me what answer you are getting for this question, guys. Okay, so if you solve using the data which we evaluated, you will get the mass of steam close to this, guys, 60 kilojoule. So if you are getting answer very close to 60, you can go with this. Actually the answer will come out 60.195 kg per second, but we can go with this D, very close to 60. So D is the correct answer for this question. Okay, now let us move to the last question and third part of this question. Again, with reference to the question number 1, determine the temperature rise of the cooling water. Take specific heat of the water is this. You know guys, in condenser actually what happens? Agar मैं only condenser consider करूँ, so this is condenser where the condensation of the steam takes place. This is the enthalpy of the steam. This is what? This is 0.4 dash. Okay, this is 0.4 dash because this is the entry to the condenser or exit of the steam. This is 0.4 dash, and what is this point, guys? This is what? This is 1. Okay, but how you are condensing the wet steam? Just you know, it is most of the steam is what? Dry only. Okay, close to 82% of the steam is dry. Remaining is what? Wet, but the mixture is what? Mixture is in the wet region. That's why I am defining that steam as wet steam. So the condensation is taking place because the steam is converting into what? Liquid. And how? Obviously you need to reject the heat to some water. So here you are rejecting heat to some water. So some water is entering. So this is the water in, W water in, या मैं इसको ऐसे लिख देता हूँ TW in. Okay, so this is water in. Okay, and water is going out. So this is TW1. This is TW2. Okay, water is entering, it is going out as water only. For water, the phase change is not taking place. Phase change is taking place for the steam. Okay, so if you want to evaluate this, the change in what? Change in temperature of the water. So whatever is the heat rejection, actual heat rejection, which is nothing but mass of the steam. Guys, this is required because we want total heat rejection. So total heat rejection will be nothing but mass of the steam which is circulating into H4 dash minus H1. These all things we know. We know how much mass of the steam, it is close to 60 kg per second. This H4 dash also we know. This is also 191.8, close to this. This also we know, guys. So we know this heat rejection. Okay, and this heat rejection is nothing but what? Mass of the water circulated into Cp of the water into change in temperature. Because whatever heat you are rejecting, this is the what latent heat change of the steam, because for steam change phase change is taking place. For water, water is going to pick the sensible heat. For water, the temperature change will be there. So mass of the water circulated, Cp of the water into delta T. So Cp of the water he has given you, I think 4.14 he has mentioned. It is otherwise you can also take 4.18 kilojoule per kg Kelvin. So this is the value, okay, delta T. And how much is the mass of water, guys? He has given you. He has given you the mass of the water circulated is close to what, 4000 kg per second. So guys, if you refer to question number 1 data, he has given you here the mass of the water circulated is 4000 kg per second. Okay, from nearby lake you are circulating the water in the condenser tube at a rate of 4000 kg per second. So this actually question I picked from the NPTEL assignment only. All questions in this booklet are from an NPTEL assignment. Okay, very good question, because we are actually getting idea of so many concepts related to Rankine cycle. How to evaluate the pump work, turbine work, isentropic efficiencies, all those things. So practice is important. So this is given to us 4000 kg per second. This is also given, and this is also known to us. So using this energy balance equation, you will get the change in temperature of the water, and this will come out close to 8 degrees Celsius, guys. Please check and match your answer whether you are getting the temperature change for water close to 8 degrees Celsius or not. Okay, so if you match your answer, you will get answer close to 8 degrees Celsius. That's why the right answer for this question will be A. The change in temperature of the water will be close to 8 degrees Celsius. Fine, guys, I hope all these 3 questions are very much clear to you. Again we will meet and we will solve some more questions from this NPTEL assignment. Okay, thank you very much. Keep revising, and for any kind of suggestion, query, you can shoot your query in the comment section. And soon we are planning to start the marathon classes also from NPTEL assignments also, and other important questions also we are going to solve from standard textbooks. Okay, thank you. Good luck. Keep preparing.